Hi, welcome. Here is a summary of the quantitative data displays activity. Depending on what mode of school you're in when we give this you may get a worksheet that looks like this, or you might get a Schoology assignment that has these questions inside of it. So we've got our northbound and our southbound data. We're going to compare. The what do you notice, what do you wonder questions, those are pretty subjective. That's for you. And there's not so much a right or wrong answer as long as you're looking at the data and you're not talking about something completely random. Number 3 is to create STEM plots for both of them. So one thing to keep in mind when making STEM plots is you don't want to see, oops, that was too heavy. You don't want to see what we see here. Right? We only have 3 stems. We've got a whole ton of data in one stem and like almost nothing in the others. This does not really give you a great idea of the data. So a good idea is to do what we did here, which was to split our stems. So I split my data from 60 to 64, the first 5, and then 65 to 69, 70 to 74, 75 to 79, 80 to 84, and then 85 to 89. This gives us a little bit better look at our data. We can see the shape of the data a little bit better, which is a good thing. Again, remember always to include a key. We did the same thing over here for the southbound data. Here's the version if we hadn't split our stems, and we like this version better. You can see the distribution a lot better. And then we created a key as well. There should have been a 1 there. Oh wait, never mind. There should not have. 60 line 1 equals 61. Okay, another option that you could have done, which would have been just fine, was to do a shared stem plot. So you could have had the northbound on one side and the southbound on the other. You would have need to have made sure that your stem went from all the way from 70 to 80, since they go a little bit different spots. One starts high and ends up higher, one starts low and doesn't get as high. So you could have done that as well to save on making a few less plots. Okay. Next page, you're creating a dot plot for the same data. So here's what your dot plots should have looked like. 1 dot is each data point. Just got to be careful when creating them, but pretty straightforward there. Here are the histograms that we made. Northbound, this one forgot to label, was southbound. And then we saw how to put these into our calculators and get some graphs back. You notice that these don't immediately look like the histograms that we made. We can see some trends, right? We can see that this one kind of looks like the same shape and this one kind of looks like the same shape, but they're not exactly the same. And if you want to make them look exactly the same, you're going to need to adjust the window, change the Y min or the X min, X max, the X scale, and the Y min, Y max. How you do that, the X scale is going to be the actual data values, so the speeds, so a speed of 62 or whatever. And on the last page, you can look and find what the minimum speed was, and then maybe go down 1 or 2 and put that as your X min, find out what the highest speed was, and put that as your X max. And then your X scale is important. Here on our histograms, we were scaling by 2s, so you'd want to put your X scale as 2. When you don't change the scale, the calculator is going to adjust its window to what it thinks is best, which can have the X scale be kind of funny, and you might not be able to see the whole graph. Remember, if you can't see the whole graph, and you don't want to go through all the work of just adjusting the window, you just want to make sure you're seeing the whole histogram, you can always hit stat or zoom 9 before graphing. Okay. Then, so we checked our work there, and when you do that, you will see that they're the same graphs, so you can feel good about these. For number 6, we found the mean, mode, and range of each of these, and then depending on your comfort level with a calculator, You can either do these by hand, adding up all the data points, dividing by the number of data, counting which one is most common, and then subtracting the biggest minus the smallest for a range. Or you can use a calculator to help you do that, either just to help you with the calculations, or you can use the one variable stats and put your data in as lists. You can see that I put northbound in as L1 and southbound in as L2. That works as well. Okay. Down here, we're making box plots. So there's some important information we need when we're making box plots. The 5-number summary and then the outlier calculations. So I've recorded the 5-number summary. Again, depending on your comfort level, you could either list out all of the numbers in your data set and kind of count in, find the median, break it in half, count in to the middle again, find your Q1 and your Q3, and you could find that 5-number summary on your own by hand. But you're more than welcome to use the one variable stats in your calculator to find it, and then just write the numbers down, which is what I did. And then once you have that, you can find the IQR, which simply subtracts Q3 from Q1, or Q1 from Q3. I'll just write that down here. And that's what I did. I took 66, which was Q3, minus Q1, which was 63. Wait, I said that wrong. I took Q3, which was 66, and I subtracted Q1, which was 63, and I got an IQR of 3. I did the same calculation over here, only my Q3 was 67.5, and my Q1 was 59, and I got an IQR of 8.5. Real quick before we talk about outliers, this is our measure of spread, so this is telling us how variable our data is. This tells us that overall, the main part of our data, the southbound, we see as more variable, and we can see that in the box plots we made, that this box plot up here is much longer than this box plot here. This one is really, really narrow. Notice I'm using the same scale. They're both going by 5s. That makes it easier to compare my graphs. I wouldn't want to adjust the X scale below because it would make it harder to do an equal comparison. But because they're scaled the same, I can see that this box is much wider than this one. So this one is more variable and we can see that in this calculation of it having a bigger IQR, 8.5 compared to 3. Okay, once we have our IQR, we can use that to do our outlier calculations. So to find outliers above our box, those would be up here. We do Q3 plus 1.5 times our IQR. So Q3 was 66 plus 1.5 times 3. Simplify that and we get 70.5. And we notice that our biggest data point, the 83, is above the 70.5, so we call that an outlier instead of extending the whisker all the way there. And then our whisker goes to the next highest data value that's equal to or under 70.5, and I believe that data point was right at 70. Then our outliers below, that would be anything happening below that bottom whisker. We take Q1, 63, and we subtract 1.5 times our IQR, and we get 68.5. And we didn't have any data values below that, so we don't have any outliers. Repeat the process over here, only using these numbers. So when we did that calculation, we got 80.25. We didn't have any data points above that, so no upper outliers. We repeated it for the bottom outliers, and we got 46.25. And again, we didn't have any data points below 55. So there are no outliers on the southbound data, but one on the northbound data above the box plot. And then we use the calculator to sketch our graph, and our graphs match our graphs above, so we feel really good about that. We didn't need to do any major window adjusting there. You don't typically need to. So we feel good that our box plots were correct. Okay, now this page is more of an analysis where we'll be looking back at our graphs and kind of analyzing them. First, We want to compare our two sets of data. And we want to compare the shape, outliers, center, and spread. So the shape of the northbound data was almost symmetric, but does have an outlier to the right. And the southbound data is skew left. Northbound data has an outlier, we kind of mentioned it earlier, but southbound data doesn't have any outliers. The center of the northbound data has a median of 65. We found that on the last page when we did box plots, and the southbound data has a median of 63.5. The spread, the northbound data has an IQR of 3 miles per hour, and the southbound data has an IQR of 8.5. So we might want to say here as well that southbound is more variable than northbound because it has a higher IQR. It is more spread out and more variable. Here are some analysis questions. So our first question says, which side is going faster? Justify your answer with evidence from your displays and summary statistics. So the first answer, which would be fair to give, would be that the northbound is going faster. But in order for you to get points for that, you would need to definitely justify why. And in this case, we can see that the median, the mean, and the max value are all higher for the northbound data. So quite a few summary statistics saying that the northbound is faster than the southbound. You also could have noticed that the mode and Q3 are higher for the southbound, and could have maybe come to the conclusion that the southbound is going faster looking at those statistics. I'm less interested in which way you actually chose versus that you were able to reference appropriate summary statistics to justify your answer. So really either of these answers would get credit. This question, what do you think the speed limit is? Justify your answer with evidence from your displays and summary statistics. This one, answers can vary, and it just depends on how you justify your answer. In this case, my first answer would be that I think the speed limit is 60. You see that some people are going slower in the southbound data. The min was 55, but the majority are going faster, median of 65 for the northbound and 63.5 for the southbound. This makes sense since most people speed by at least a few miles per hour, right? The speed that people are actually going is typically going to be a couple miles above the speed limit. And so if we had said the speed limit was 65 because of the median, you could say that. But what we know just about human action is that they're probably, if they're going 65, the speed limit's probably slower than that. I really like question 3, or C. It says, do you think this data is a good measure of what speeds are usually like on this road? And you could think about it in a couple of ways. You don't necessarily know what time the state trooper was there, or if he was using a good random sampling method or anything like that. There could be issues with his data. But the big thing that we absolutely know is getting in the way of accurate data is that there's a state trooper taking speeds. What do people do as soon as they see the state trooper? They're gonna hit their brakes and slow down. This could also explain why some cars are going in one direction are going faster or slower than the other. I would guess that maybe from one direction, probably the southbound, you could see him sooner. And so those cars are having more time to slam on their brakes and slow down than the northbound cars. And that might explain why the distributions look pretty different. Okay, next question, D. What measure of center do you think is most appropriate for each distribution? Remember, we look at the shape of our distributions. So the northbound data, remember up here, the shape said it was almost symmetric. So symmetric data, a mean is good. We would want to take out that outlier before we used the mean, because that will skew it, since it's almost symmetric. So I would take out the outlier and say almost symmetric, or if we left the outlier in, we could use the median, because that would not be skewed by that outlier. And then the southbound is very skewed left. We would want to use the median. Lastly, which measure of spread do you think is appropriate for each distribution? Northbound, it's almost symmetric, so if we take out that outlier, we could use standard deviation, which was around 4.8. Southbound, because of the heavy skew to the left, we would want to use the IQR. Awesome. Thanks for watching.